Okay, hi folks. This is the first of the series of videos for probability and random variables for sections 4.6 and 4.7. Before we get into the specific distributions in those sections, first thing we need to talk about is the kernel, what's called the kernel of a distribution. The kernel, and as I go through these, I'll be making comments. I won't be reading them verbatim. On occasion I will be, but just so you know in advance. As it says here, the kernel is the portion of the probability mass function or probability density function that is a function of the random variable. It does not include the constant. So I've given you some examples here. For example, in the geometric probability mass function, the portion q to the x minus 1, that portion is a function of x, whereas p is just a constant. So with the Poisson, the e to the negative lambda is a constant with respect to x. So the kernel is the portion lambda to the x divided by x factorial. For the normal, the kernel includes everything except for 1 over root 2 pi times sigma. And then for a distribution we haven't talked about, but it's a little easier to work with to introduce the concept, something called Pareto. The one parameterization of the function you see there, alpha times beta to the alpha divided by x to the alpha plus 1. And as far as the density function is concerned, b is greater than 0, alpha is greater than 0, and I made the mistake of not writing that x has to be greater than b in terms of the domain. So that's b is identifying the lower bound on the random variable itself. So now the purpose of talking about a kernel is the fact that at times it's going to make things a little bit easier in terms of the integration of the summation, but we know that the sum or the integral of the mass or PDF is 1. So if we were to take either the sum or the integral, depending upon whether we're discrete or continuous, of the corresponding mass or density, of the corresponding random variable, then that summation or that integral is equal to 1 over the appropriate constant. And as I noted here, please note that that's not a correct mathematical statement. I'm just trying to give you an idea of what's going on. Sorry about the upside down. I'm getting all kinds of warnings with YouTube like that. So here are a couple of examples. In the case of the geometric, if we take the summation of the kernel, we have that geometric series there that works out to be 1 over 1 minus q, which is 1 over p. Remember, the constant we had for the geometric was p, so the reciprocal of that is 1 over p, as you can see. For the Poisson, right there we've got the summation x equals 0 to infinity of lambda to the x over x factorial, and as you learned in Calc 2, that is the power series expansion of e to the lambda, and that is the reciprocal of e to the negative lambda. In the case of the Pareto, as you can see right there, if we take the integral from b to infinity of our kernel right there, we end up getting 1 over alpha times beta, times b to the alpha, and again that's the reciprocal of the constant. So we're going to need that pretty soon in a couple of pages. So, but it's better to just talk about it now in a general context. Okay, so that brings us on to the gamma distribution. You've got the density function there. You'll notice it's got 2 parameters, both alpha and beta, in it. So you've got the functional form there. And please notice that there's a power function term and an exponential term. As far as the variable and the parameters are concerned, they all have to be greater than 0. I've got some basic properties there in terms of the shape of the distribution and a couple of the homework problems. ask you to go to the applet site. Remember, I gave you the link on the syllabus. And what you're going to end up doing is changing some of the parameter values to be able to see 3 different gamma densities printed or graphed on the same scale. So you've got that for homework. You don't have to turn in any printouts with regard to that, but you do need to pay attention to what's going on in terms of the shape there. So please make sure that you do that. Okay, now just a little bit of the discussion on this next page, but a couple of things to notice here is one of them is for a given value of beta. As you increase alpha, you'll notice that the peak or the mode of the distribution, the peak, moves down vertically, and also the mode moves out to the right. Moreover, the distribution gets more stretched out, so our variability is going up. But the other thing is that there's less skewness. Now, one of the other things to notice here is if you fix alpha and you change beta, you get a similar type of impact, but for the same types of changes, you won't see as big of a decrease in the skewness. One other important thing to note is that remember that alpha has to be greater than 0. So when we go back to the density function right here, you'll notice if alpha is between 0 and 1, then we've got y to a negative power. That's one of the reasons why that we've got this y is greater than 0. If alpha is 1 or larger, then we can actually put the or equal there, but because we're working with alpha greater than 0, we have to limit that to the set of positive y's. Okay, so what I've asked you to do is to go ahead and enter 0.05 for the value of alpha and see what happens with the density function. So there's a little explanation there for you to follow. Okay, now for some of you, depending upon what you've had, you may have seen something called the gamma function, which kind of looks like hangman of alpha right there. And it does come up in some other classes, but we're going to give you a little introduction here. Sorry for the scribbles, mistakes in writing this up. So first off, as far as the definition of the gamma function is concerned, it's an integral function. Gamma of alpha is the integral from 0 to infinity of x to the alpha minus 1 e to the negative x dx. You'll notice that that looks an awful lot like the kernel of a gamma distribution, but we've got e to the negative x as opposed to e to the negative x divided by beta. So, okay, as far as properties are concerned, some important things that we're going to use throughout this. First off, if you evaluate gamma of 1, plug it in and do the integration, you find out that's equal to 1. Secondly, gamma of alpha is equal to alpha minus 1 times gamma of alpha minus 1. The derivation's in the book. I didn't write that up. It does require integration by parts, but one of the things that you do find out with regard to all of this is that you end up getting a recurrence relation, and a big result is that if alpha is a positive integer, then gamma of alpha is equal to alpha minus 1 factorial. That recurrence relation is used on the next page to show how this works out to be alpha minus 1 factorial. I'll leave that for you. The last one that we don't go about proving in this class but can be nice in certain circumstances is that gamma of a half is equal to the square root of pi. That is a Calc 3 problem. It's effectively or Calc 2, depending upon where you saw polar coordinate transformations, but that's where that comes from. Okay, so first off, coming up with the value of the constant here. I've given you 3 different gamma distributions. The constant C is not calculated here, but all 3 of these have gamma kernels. And so first thing we're doing here is identifying what the values of alpha and beta are in these cases. So in the first case, we've got y cubed e to the negative y over 4. Remember, as far as the power function is concerned, it's y to the alpha minus 1. So the value of alpha in that case would be 4. And then we have e to the negative y over beta. Beta in this case is 4. So we have alpha's 4, beta's 4. In the second case, we've got y to the 0.8, so alpha would have to be 1.8, beta's going to be 5. And then in the last case, we've got y to the 1.5, so alpha has to be 2.5, and beta has to be 2.4. Okay. Pardon me here, let me slide this up a little bit. Okay, so it basically becomes a matter of plugging the values into the 1 over gamma of alpha beta to the alpha to calculate all of these. So as far as number 1 is concerned, calculations are over here. We've got 1 over gamma of 4, 4 to the 4th. Remember, gamma of alpha, when alpha is an integer, positive integer, is alpha minus 1 factorial. So the calculations worked out there. It's 1 over 1536. I did number 3 next. Number 2 is on the next page. For number 3, we've got gamma of 2.5 times 2.4 to the 2.5. Now, because alpha is an odd multiple of a half, we can use property 4, which is right there, as well as property 2 to actually get a value on this without having to do any integration. So using the recurrence relation, we have gamma of 2.5 is 1.5 times gamma of 1.5. We then need to use that again. Gamma of 1.5 is a half times gamma of a half. And remember that gamma of a half is the square root of 0.5. So if we multiply all of that out, which is right there, you're going to get 1 over slightly more than 11.86. Sorry if you hear the dog in the background. Okay, now the last one, which was actually number 2, this is 1 over gamma of 1.8 times 5 to the 1.8. Well, we can get 5 to the 1.8 off of the calculator. Gamma of 1.8 we can't do directly using our other rules. We actually have to use the definition. Now, by the way, if you're using Wolfram Alpha, there actually is a gamma function. So you could type in gamma function of 1.8 and it would give you this value, but I also need to show you how to do this for your exam purposes. So we're going to actually substitute the 1.8 into the definition of the gamma function and go through the integration. The problem is that as far as the TIs are concerned, it has a lot of trouble with doing this integration, especially on the 83s and 84s, but I've seen trouble on the 89s as well. It turns out that if you try to go 0 to infinity on any of these calculators, you end up getting some weird outputs. Sometimes it'll tell you it's 0, and you actually have to lower that upper endpoint to something a lot smaller. So the easiest way to go about doing this is to use an alternate definition of gamma of alpha, which is right here. It's the integral from 0 to 1 of the natural log of 1 over x raised, all raised to the alpha minus 1. If you do that, I've never had an issue on the calculator getting the value out. So if you were to go ahead and plug this into your calculator and do the integration, you would end up getting the 0.931384 that I've listed up here, and then you can just plug that in and multiply it by 5 to the 1.8 to get our 1 over 16.8762. Okay.